During this session, I'm going to try and explain or show the types of calculations that you might have to do when you're working out a certain specific heat capacity. The idea is that I'm going to quite quickly go through some examples, and these are things which will be very useful to review when you're required to doing these calculations themselves. The first example I'm going to use is how you'd calculate the specific heat capacity of a liquid. You're probably going to use a setup which looks a little bit like this. Here we have a thermometer for recording the change in temperature, a calorimeter, which is a device for holding the liquid, and it's normally made of a known single material, and it was designed to absorb as little energy as possible to have the smallest impact. A heating coil, this will be using electrical energy to produce and transfer to heat. The unknown liquid, an insulator of some sort, so therefore as little heat energy is lost to the environment to make your experiment as accurate as possible. A stirrer to make sure that the energy is evenly distributed around the liquid. And you'll also have either a joule meter or a voltmeter and ammeter, which will help you to calculate the amount of electrical energy which has been provided to the liquid. So the calculations that you're going to need. First of all, you're going to need to work out the electrical energy. So this is in theory, should be equal to the thermal energy gained by the liquid and the calorimeter, assuming that no energy is lost to the wider environment. Electrical energy is calculated by the voltage times the current times the temperature. And it's expected these to be the voltage and the current will be constant through the time taken. Sorry, T is time taken. This should be equal to, so the energy going in should be equal to the energy gained by, first of all, the liquid. So this is the mass of the liquid times the specific heat capacity of the liquid times the change in temperature. And the energy gained by the calorimeter, the mass of the calorimeter, the specific heat capacity of the calorimeter, and the change in temperature of the calorimeter. How this calculation will work. Using the conservation of energy, we recognise that the electrical energy going in should be equal to the thermal energy gained by the liquid and the thermal energy gained by the calorimeter. This gives me an equation: voltage times current times the time, multiplied by mass of liquid, specific heat capacity of liquid, and change in temperature of liquid, plus the mass of the calorimeter times the specific heat capacity of the calorimeter times the change in temperature of the calorimeter. Now, here the only unknown in an experiment, if you did it thoroughly, would be the specific heat capacity of the liquid. So let's look at an example of this. I've got a 240 volt electrical heating element which is going to be used to heat the water. The temperature of the water rose from 20 to 50 degrees centigrade in 4 minutes and 20 seconds. During the heating process, the current flowing through the heater was 3.54 amps, and we've been asked to calculate the mass of the water. So this question changes the unknown to the mass of the water. As we're using water, we know the specific heat capacity, and this is something we can look up. Other things to notice about the question. Please remember that the change in temperature is going to be 30 degrees. And remember, although the time is given as 4 minutes and 20 seconds, this has to be converted into seconds. So let's start to map this out. First of all, we initially work out the amount of energy which has gone in. We know that the power rating is going to be 850 watts. We know that the amount of time is 260 seconds. So in total, 221 times 10 to the 3 joules has been provided, has gone in to my system. With this knowledge, I can then recognise that as I know the specific heat capacity of water, which is 4,200, and the change in temperature is 30 degrees, then I can from rearranging my specific heat capacity formula, I can work out there is 1.75 kilograms of water involved in this situation. When thinking about solids, I can make my measurements directly. So if I have a block of material and I make sure that this block has two cylindrical holes drilled in it, one for the thermometer, one for the heater. So with a solid, I don't need to have a calorimeter. So in this situation we have a very similar question. An 850 watt heater is placed into a hole in a piece of copper of mass 1.75 kilograms. Calculate the temperature rise in copper if the heater was left on for 4 minutes and 20 seconds, and then calculate the final temperature of the copper if the heater was left on for 10 minutes and the copper was originally at a temperature of 65 degrees centigrade. So two questions here, both looking for a different unknown, but still using the same specific heat capacity formula. For question A, I know that the amount of energy transferred into the copper is 221 times 10 to the 3 joules. Here, if I rearrange the formula, I can work out that the change in temperature is going to be 324 degrees centigrade. For the second part of the question, the energy transferred to the copper is going to be slightly greater because it's on for a longer amount of time. So I've got 510 times 10 to the 3 joules. And in this case, I can work out the change in temperature is going to be 747 degrees centigrade. Remember, if I was looking for a final prediction of the temperature, I'd have to add that to the initial room temperature. So in this case, the final temperature is 65 degrees plus 747, which gives me a final temperature of 812 degrees centigrade. Another example. Okay. In this case, you've been asked to calculate the specific heat capacity of an unknown substance. I have a mass of 100 grams of this unknown substance, and it's heated to 260 degrees centigrade. The block is then placed in a beaker containing 500 grams of water at 20 degrees centigrade. After some time, both substances reach an equilibrium of 30 degrees centigrade. Find out what the specific heat capacity is. So the idea in this situation is I have a hot object which I'm transferring my energy from that hot object into the water. So the idea is that the energy transferred out of my hot block is going to be the same as the amount of energy gained by the water. And that's the essence of this question. So here, energy gained by the water is going to be equal to the energy lost by X. So this is another way of calculating the specific heat capacity. What I've got here is if I look at my two calculations, first of all, the change in energy of the water. The water has changed by 10 degrees, and I know exactly the mass of the water is 0.5 kilograms, so I know the specific heat capacity. My hot block has changed from 260 degrees down to 30 degrees, so a change of 230 degrees, and I know that the mass of the block is 0.1 kilograms. So that allows me to work out the specific heat capacity of that block as 913 joules per kilogram per change in temperature. Again, we're still using the same specific heat capacity, but here we're saying energy gained is equal to energy lost. Similar couple of questions. How much energy is needed to gain? So please take your time going through these questions and solutions, just working through. I'm not going to talk through those. I'm going to allow you to review those in your own time.